Hello again.
Hi. Hi, Jan. We're just waiting for people to come on now.
Sorry?
We're just waiting for people to come on now. So we are live.
Oh, hi.
Can you see the screen, Jan?
Yes, I can see it.
Great. Great.
Okay, but I am again not able to share a screen.
Not okay. You will now.
Okay, now it would work. Thanks.
Okay. We're just waiting for everybody to come on, and then yeah, we'll kick off. Give them just a minute. Okay, I will share my screen. Just got a few people to come on yet. Looking at the list.
How many will it be?
Over 20.
Okay.
Okay, it's 10 o'clock. Welcome everybody. Thanks for joining the call. I'm Jonathan Brindley from JB Unmanned Aerial Systems, and being joined today by Jan Coqueget from SENSYS, who is going to be running through some data for us and filling in some gaps for me as well. As you might be aware, the SENSYS R1 is a new product development by SENSYS, and yeah, it's proving pretty good. So let's move through the slides anyway. As the first slide says, this is the R1 solution for the M300 M350. So that's not to say it can't be used on other drones, but obviously today this is going to be revolving around those two types. I think a lot of people in the industry have got the M300. I think more and more people have also got the M350 as well. So let's move on to the agenda. So going to be about a bit about JBUS, look at the solution itself, what the component parts are. We're going to delve into SkyHub and the Custom Payload Monitor, which is the interface for SkyHub, and how that all comes together with true terrain following so that we can keep the drone just above the ground. We're going to then look at some of the detail on the MagDrone R1 in terms of specification. Quick review of applications. That's just a single slide, so we should be able to breeze through that. And we will then take some time to look at the how we download the data, upload the data, and Jan is going to give us a quick whirl of the SENSYS data tool. So after that, Jan's going to take us through the R4 versus the R1 and what the data says and how they compare. Very interesting. I have had a peek preview, so that would be good. And then yeah, we'll have a quick word of just a quick word about SENSYS Magneto at the same time, and then we'll have a Q&A. Okay, so a little bit about JB Unmanned Aerial Systems. A lot of you by now would know that we've been operating for about 3 years now. We are distributor and / integrator for SBH Engineering, and work really closely with SENSYS on all their airborne magnetometer systems, such as the R1, the R3, and the R4. And of course, others that come in the future as well. So working really closely with both with SENSYS as their OEM and also SPH in terms of their UgCS SkyHub True Terrain Following Radar and how we bring it all together to provide a solution. So a little bit more about what we do here. So yeah, we're not just all about magnetometry, but with our friends at SENSYS, but we also are involved in demonstration trials for GPR systems. We have trials and demos for methane outstanding at the moment. We're working on with companies that are looking at echo sounders and water sampling systems for projects, and we also deal with workflow for the thermal systems. Two of the sensors that are fairly new is the metal detector system, which is still in development, I believe, and also the water velocity radar and water level radars, which are in development as part of a European project, and hopefully they'll be coming out quite soon. So just watch this space. So we have a wide range of geophysical sensors and kit, and if you think we can help you with that, then please, get in touch. Just to bring your attention to JBUS's Test and Open Day, as some of you might be aware, we do now have a test and training center, which is dedicated to flying geophysical sensors. So we don't do above the ground. We are strictly geophysical, strictly systems that are looking at the ground. So yeah, if you would like to come along to the Open Day in September, that would be great. It'll be 9 till 4, and we will have SENSYS and UgCS there, or sorry, SPH Engineering there to support us. We hope to have a heap of sensors. We'll be running through the SkyHub and the True Train following, and we'll be able to answer any questions you've got on the day in terms of how it all comes together and availability of sensors. For those that aren't aware, about the test center itself, we do have classroom facilities. We also have a true terrain following course, which we put together, which kind of it's a good place to show how the drone and the TTF work together hand in hand, certainly from the object mitigation sensors that it has on board. So, and we also have laid down areas for targets where people can bring their own targets along, and we also have our own buried section to quite a few buried targets up to 0.5 meter, which we've already got in the ground, and people are able to go along with their handhelds and compare their handhelds to the airborne variant. So and lastly, yeah, we've got the ability to, with a 30-ton JCB on site, we're able to dig large units into the ground, large targets, I don't know, say 250 kilograms for one of a weight of ferrous material into the ground with certain backfills, and so we can accommodate that kind of project. If you need to prove something, then come along and give us a call. We'll see what we can do for you. Okay, so a little bit about LinkedIn, because it's just the center where we're posting most of our demos and trails. If you're not following us already, go onto LinkedIn, JB Unmanned Aerial Systems. Follow us. We put all our projects up there for demo and trials, what we can do. So, for example, on the left here, we've got GPR for bathymetry, which was a trial in Scotland. We've got a echo sounder trial for dikes that some people might have seen that we did recently with a geospatial consultancy. And on the right here, we were visited just this week actually by UxO consultant in the UK with real munitions, or as real as you can get with not being live anyway. To trial out different systems to see how we could help them. So yeah, keep an eye on the LinkedIn, and there's always some good stuff in there, and yeah, it'll keep you informed of what we're doing. So that's a little bit about us. So let's crack on with the what we're really here for, which is about the new R1 from SENSYS, and start with just have a quick look at the solution components. So the first thing to say is we're talking about a solution here which is made up of two main parts. The first part is the SkyHub and True Train following kit. That's the bit that takes data in, and it allows the drone to fly at the height we want it to. And that's by SPH Engineering. And then we've got the second part to it, which is the main part, if you like, which is the actual magnetometer itself, which has been designed by SENSYS. So let's just have a look at how things come together on the drone. So this is an M300, and you can see that we've got the TTF radar at the front that fits in to the gimbal mount. We've got the SkyHub or onboard computer, as it's known, and we'll go into that in a little bit more detail in a minute. We've got the MagDrone R1 that is situated below, which we attach via a heavy payload attachment, and we have an OSDK smart cable which is sending the data into the SkyHub from the M300, and data is being transferred between them. We're also taking power from the drone using that OSDK and placing that into the drone. And in this case, you can see it's a development version. It's been split into the R1. So that's essentially what it will look like from the side. That's how it would look and how it would set up. Last thing to say is, I nearly forgot, is I did mention it briefly. The data is transferred from the R1 via the USB connection at the bottom of the SkyHub, and you can just see that at the bottom there. It's this cable for data. So that's a USB connection going in. So we've got power on the right, and you can see data below coming out, the cable going into the R1. So let's talk a little bit about SkyHub and the CPM interface. So what's SkyHub? What is SkyHub? Right, so SkyHub's role, it's an onboard computer, and it's talking to the M300 RTK, so it's exchanging data. It's also got a role of syncing the UgCS Pro and the true train following. So it's bringing the two, and we'll talk about this a little bit later, so bringing software packages together and knitting it all together nicely. So it's doing a lot of the knitting. It's managing the object detection radar. So if we've got not just the TTF radar, we're also, if we are doing MAG or GPR at low level, there are instances which we found where the onboard object detection of certainly of M300 and M350, it's not 100%. So very small upstanders and small branches, when you get to the edge of your lines, you can actually find that if things aren't judged correctly, that the drone isn't seeing these very thin items. So the object detection radar, which we'll have a look at later, is just another safeguard that we can put in place that gets around that and obviously protects the drone. The other role of SkyHub is to provide the power to the R1, and also to receive and fuse the R1 data with telemetry. So this is where we deviate from the R3 and the R4. Those who know the R3 and the R4 will know that the data is essentially recorded in the R3 and R4. It's not, we don't take the data like we do some of our other sensors and feed that into the SkyHub and then fuse that data. That's not what we've done with the R3. The R4 work by, we'd send an RTK signal for GPS correction into the recorders of the R3 and the R4, and then we just download the R3 and R4 data from the R3 and R4. That's how it's been done. The R1 is the first system, if you like, where we are taking the data into SkyHub and we are fusing it in SkyHub. So that's where it differs for the first time. So we're taking telemetry from the drone, we're taking data from the R1, and we're fusing it within SkyHub and creating a CSV file, which is then uploaded into the data tool, which is a free software from SENSYS, which just makes the processing just really easy. So I mentioned about SkyHub and CPM. So what's CPM? CPM, Custom Payload Monitor, or as I started out calling it, Custom Payload Manager. But whether it's Manager or Monitor, that's down to you. But essentially, it's the interface for SkyHub. So when you fly using the SkyHub, you will need to interface with it in some way whilst you're watching it fly and wanting to interact with it. And there's a picture there on the right-hand side. You can see the general kind of look, how it would look on your laptop. But essentially, its role is to enable the flight algorithms. So whether we're enabling true train following, whether we're enabling other algorithms like Grasshopper, for those who know about echo sounders and how we use the Grasshopper with echo sounders. It's there for us to set the safe and the target heights. We choose the sensor widgets within the CPM. So if we're flying GPR in this case, as an example, we can go in, click that widget, and that widget then allows us to see the live data come in. So that is just so to be clear, that is a live data stream coming in. And we have that ability on the R1 as well. So also CPM allows us to download the data files directly from that. And like I said, there's a heap more. But essentially, it's simply put, it's the interface for SkyHub. It's how we interact with SkyHub when we're flying our surveys. It's a very simple tool, and it integrates with the UgCS Pro. So talking about integration, so here's an example here on the screen of how it would integrate. So normally you would just fly it on with CPM on the left-hand side of your laptop, and you would fly with the UgCS Pro or equivalent on the right-hand side. As you can see, what we're doing on the right-hand side is we're setting speed and our flight plan. So where are we going to go with the R1? What speed do we want to go between the waypoints or for the survey? And that's set in UgCS Pro. In CPM, which will be sat, as you can see, just next door to it on your laptop, we're setting the target altitude and our save altitude. So essentially, they're the main parameters that we're setting before we activate the true terrain following or the mission within CPM. And that, again, if you can imagine, you can see there, read, configure, and activate. Once we've uploaded our mission in UgCS Pro, that will allow configure and activate to become available. We're able then to activate. But until we've uploaded the mission, we are not able to activate. So a little bit of a safeguard there. But it's a very, they work really hand in hand, and it's seamless. So let's have a look about how it all comes together. There's a number of steps we can do quickly for the M300, M350. We're connected in the OSD cable. You can see the 1, 2, and 3 lights in the bottom hand corner. That's given us indications that when the system's set up and it's powered on, it's telling us essentially where it is in regards to its ready state. So it will go through flashing 1 to flashing 2, and then when we get a flashing 3, it's telling us, look, I'm ready to go. So it's almost like some diagnostics of where it is at that moment in time during its boot up sequence, and it can also give us ideas on what's wrong with the system. If we've not got something connected up properly, or we'd not update the software or something like that. So there's a really good video on our YouTube channel, actually. If you go to the JB Unmanned Aerial Systems YouTube channel, there is a nice video there that will go through the 1, 2, and 3, so that you can use that if you get time. So you can see on the right-hand side, so we're connecting up the SkyHub for data and power from the M300, and you can see on the right-hand side there, as an example, we have a cable coming in on the right-hand side of the SkyHub. That with the orange connector, that is the power coming in, and on the top, in this particular case, this is the normal way we would do it. Obviously, with R1, we're at the moment on the development phase, we've splitted it out. And then we've got data coming in at the top of from into the SkyHub from the M300. That's how it would be connected up. And then the next one is to connect up the true terrain following. You can see the picture on the left-hand side of the TTF radar there on the front of the drone there on the gimbal mount, and that is also being connected in via this yellow connector on the right-hand side picture. So again, very easy to connect in. They are color coded, so it's not like you can really go wrong. Yellow to yellow, red to red, and so on. It's a very easy setup. I mean, I think of all the main message from all of this is I mean, don't get too bogged down with the specifics. It's really about how simple it is. It is basically plugged by colors. So it's a very simple process. In this particular case, we're connected up the R1. As I said, this is a development. I'm sure this is going to be tidied up somewhat, but in the first instance, you can see that we've got power and data. We've got data at the bottom, and we've got power going into the R1. Step 4, I talked about the connecting the obstacle detection radar for small stand-ups earlier. Again, it is an option. It's not like you have to. But it is recommended if you are flying low missions at a meter. Certainly, it's a good safeguard to have in place. Again, comes with a white connector, a white band around its connector, and again, there's a white connector, female connector on the top of the SkyHub. Again, it's connected by colours, and it's really straightforward. That would be set up in the CPM again, just as we did before. And then the last stage here would be step is just to sync up the software. So it's good just to touch on the 3 bits of software that we have that all come together to allow surveys to happen. We have the UgCS Pro, which we've mentioned already, which gives us the mission and the speed. Where do we want to go? What do we want us to be? That's all done on the UgCS Pro on the right, and on the left you can see there, Custom Payload Monitor is where all our widgets are, where we can see live data coming in, where we set the height and our save height. So and then the last bit of software is just like your DJI equivalent on your controllers. We have a UgCS Pro, what's called UgCS for Android companion, and when you upload your missions in UgCS Pro, it also loads up onto your controller, which you'd expect. So you've got some context to what you're doing and being able to fly to the first waypoint. This is a seamless link. It all links together, and it allows you to fly your mag surveys with the R1 or the R3 or the R4. You're setting it up really quickly. So a little bit about the SENSYS MagDrone R1. So a little bit of the technical. Standard sampling rate is 250 hertz. I mean, fast. A lot, which means you can fly quite quickly. It can have up to 1,000 hertz sampling rate. If you've got a really fast computer, that'd be great. But standard out the box, it's 250 hertz. Noise level. Remember, this is just the sensor. When you put the sensor into a system into its casing next to the drone with all the other factors, it's not the full picture. But certainly from a technical perspective of the sensor itself, then 10 picotesla is kind of noise level. Remember that the sensor is over 1.2 meters away from the drone. Those that know the R3 and R4 will know that the R3 and R4 are in a horizontal plane directly below the M300 and 350. They're very close to the electronics of the drone, we can filter out a lot of the noise away. But what that is basically giving us is that 1.2 meters is giving us a higher amplitude, which is resulting in lower noise, and smaller items are being detected, and that shows up in the data as well, which Jan will go through a bit later. Okay, another little bit of detail there on the sensitivity of the default sensor, but I mean, like we said, there's a lot. This is for reference. This will be put on our YouTube channel. You can go on and you can go on and look at this as much as you like, but it's just a bit of technical there. Resolution of more than 150 picotesla, and with a measurement range of plus or minus 75,000 nanotesla. Those who know about Fluxgates will know that it measures in the X, Y, and Z. So you're able to split all that out, essentially, the X, the Y, and the Z. So it's to enhance interpretation. Jan can talk a lot more about on the technical side. If you've got Q&A, we've got a Q&A at the end. Please ask questions as we go along. We'll answer as many as we can. And then Fluxgates, which some people will be aware on the call, they're omnidirectional. So you don't have these issues with the orientation and location as you move them around. They don't have that problem. So some physical dimensions. So you can see there. I mean, the key one that I've mentioned already is that when you work out, when you get your measuring stick out and you measure how far away that single sensor is from the from the drone, it's over 1.2 meters, and that's the difference that you're getting from the R3 and the R4. It's much further away from the drone, and you can see on the right hand side a picture there of how it looks. So a little bit about flying the R1. I've set it up a few times now. I'm setting it up in less than 10 minutes. And that's with the software as well. So UgCS Pro and all this kind of stuff. I'm setting it up quickly, and I admit that I've done it a few times now. But just if you were going to buy this kind of kit, you could also do that. You could hone in on how making it as efficient as you can. The R1 weighs in really fairly light, even with the UgCS SkyHub TTF integration, which gives it a 35-minute flight time. That is actually very realistic. Work off 35 minutes. I wouldn't say. I mean, if it's gusty conditions, then it might be a little bit different. But you've got some slight breeze or whatever, and you should manage 35 minutes without a problem. The other great thing about the R1, of course, is it's 1.2 meters away from the drone. The drone is quite safely away. It's got time to react and so on, but I've flown it at tens of centimeters above the ground, and like we said before, that's giving you higher amplitudes, lower noise, and being able to detect smaller items. That's what it's giving you. Buying the R1, seeing despite it having only a single sensor, flying it at sort of 10 to 15 centimeters, it's pretty remarkable. It does bring a smile to your face, because you know that's giving you a lot more than what you would get with some of the other systems. They have their advantages, and obviously the R1 has it as well. So yeah, high sampling rate. It's just like the R3 and R4. It's still 250 hertz, so you can fly quickly, and you can maintain a high data quality. So just some examples here of what I've put together here. So flying at 5 meters a second with a 0.5 meter swath. So you're looking at about 1 hour 20 minutes, including battery changes to do 1 hectare. I'll let you read the rest of them, but you can see that's not stupid time. We're still cracking on with time, still getting through to get the reduced noise, the higher amplitude. That's probably that's really good, and you can get through a hectare in no time at all. So some of the trials that I've been on, that kind of area in that time is, that's really good. So again, it's down to the risk profile of the pilot, of how fast he wants to go. But being so far off the ground with the drone just gives you a lot more. Reduces the risk profile. So that's one great thing about the R1. So a quick review of some of the applications. All these will be familiar to you, anybody that's dealing with magnetometers, but those who are coming into this for the first time, the obvious one is UXO. Magnetometers are being used on a drone, are being used by many UXO companies. But like I said, higher amplitude, lower noise, smaller object detection. You can be 10 centimeters off the ground with this system. I mean, that's great. I mean, that's really good. That's ideal. Mining applications, people will be aware of that. Detected kind of buried tanks, concrete, steel, all this sort of stuff in the ground. Mapping ferrous utility pipes, mapping power cables. I'm sure there's at least about 1 or 2 companies out there that have spoken to me before about a system that could do this. I kept telling them to wait. So hopefully, if any, I think one of them is on the call. So we'll be talking after no doubt about this. Mapping Archaeology, I think that's worth a trial. If anybody out there would like to trial the system, I'm sure we can sort something out. So come and see me, and let's try and sort something out. And if you can't, we are certainly going to have this at our open day in September. So come along, and we will have that system out, and we will show you what it can do. Like I've already said, Jan is going to take us through some comparison between the R4 and the R1 anyway. But yeah, you know, if you can get to the September open day, please come along. It'd be great to see you. And we're offering a free buffet lunch. So what more do you want? Lastly, on there, artifacts and buried infrastructure, walls, pits, and ditches. Like we said, lower noise, high amplitude. You're closer to the ground. You know, you're getting better results. Again, for those that aren't aware, just like the R3 and the R4, magnetometers aren't affected by water. So you can have a pond or a bog. It's, you know, 0.5 meter of water, and you've got something under that. The magnetometer will fly over the water without a problem and give you the same results as you would get, but you know, very similar results that you would get if you were going over land, for instance. So water is you know, doesn't really affect the outputs. Okay, so download and data processing. And this is the sort of place where I will I'll get Jan to take over in just a moment. But just before we do that, just to let you know how we actually download the data. And like I said, this is the first time SENSYS are sending data into SkyHub. Before, like we mentioned before, R3 and R4 own data recorder. We download from those systems. Now we're taking the data into SkyHub. So the way that we download data, we save it as a CSV, and it's then we've got two ways of downloading it. We can either go directly via SkyHub into the tool section, and we tick CSV. We say today, I don't know, maybe we've done 5 flights today, and it will just download 5 flights from today, and then we now download. We deal with them and manage them in the normal way into our files and so on. The second way of doing it, and this is when you become a little bit more competent, when you want to see other files as well, like positioning files from SkyHub, where it's recording all the telemetry. You can go in via WinNCP via the file client, and you can download the data from there as well. So there are there's a couple of ways you can download the data. And then once we've got that CSV file, whichever way we've used, we're then uploading that CSV into the data tool. And the new, and Jan's going to talk about this now, so I don't want to steal his thunder, but the new data tool, which has been released, which has got some new features, which are really useful. The new tool allows you to upload a CSV in the R1 format and process it in the normal way, which is great. For those that are familiar with data tool, I mean, the process flow is really good, and it hasn't changed that much, which makes it just taking on the R1 really quite easy. Last point there at the bottom there is that there's different file, you can export to different file types depending on what your needs are. So if you want raw files, you want to clean it up slightly, or clean the lines up and then output that. You want to output it to ASIS montage and so on. You've got different ASC types for that as well. So really useful tool. Right, so Jan, do you want to give everybody a quick whirl, like a 5-10 minute whirl of SENSYS data tool?
Yes. Thanks, Jonathan. I hope you all can see my screen now. I'd like to show how to pre-process the CSV file, which is downloaded from the SkyHub. So let's check this out with the brand new MagDrone data tool 3.4, which now allows to import these CSV files of the MagDrone R1. So I think you know it from the R3 and R4. So, and to import R1 data, you have to choose the CSV button here and choose your file. And in general, the processing is really completely the same as with the other MagDrone systems. So I don't want to go here too much in detail. I just want to show you how to process the data with the default settings. So as you know, the first step to do is always the track detection. I just let the default settings here, so just click detect, and we have 12 tracks. So this is a sample record of our SENSYS test field. So first step, the track detection, and then some words to the default filtering you have to do. The important filter is smoothing filter, because as Jonathan already mentioned, there's a lot of noise from the drone, even if it's far away from the drone, but you still have noise from the drone, and of course environmental noise, whatever. So you have to smooth the data. And another important step is the compensation, because what we are measuring is the Earth magnetic field, but what we want to analyze is the anomaly of it. So we have to calculate out the Earth magnetic field to make signatures visible and analyzable. A default setting here is for UXO detection, a moving median with a window of 15 meters. But if you do exploration flights or whatever, you should use constant median or overall median. Of course, you also can do noise and frequency analysis here. Just a sample. That's the frequency of the raw data. You can see our 50 Hertz power frequency. And that's just to check if you have any problems, what could be the problem. But for data processing itself, you really just have to check the settings and click export. And a few seconds later, depending on the area, you will get the preview here with the scatter plot. And you
Jan, there's one quick question whilst you're doing that. One question's come in and saying that is it possible to see the raw noise or the raw data of the noise?
The noise of the raw data, of course. Here you can see just the noise of the complete measurement. So it's in this case about 60 nanotesla, but I will come back to this point later.
Okay, brilliant.
Okay, so that was already the quick reprocessing of the data in the tool. So you get a first result, a first picture of the data, and in this case you get an ASCII file for further processing in Oasis Montage or whatever. Of course, you also can use Magneto for that. But at the moment it should be enough for the data processing. Now I would like to compare the R1 and the R4. So Jonathan, could you please start the slides again?
I can. Hopefully people can see that. Can people see that?
I think now we can see it, yeah.
Okay, there you go.
Okay. I want to start with an important fact everyone should know. Not only the magnetic moment of an object is crucial for its detectability, but also the distance between a sensor and the object. To clarify that, you can see a small animation here. Jonathan, could you play it, please? It's showing MagDrone R4 records. of the SENSYS test area in 3 different flight altitudes, 2 meters, 1 meter, and 50 centimeters. And of course, the closer you are to the ground, the higher the amplitudes become, and the more smaller objects become visible. Next slide, please. So let's start to have a closer look to the MagDrone R1 compared to the MagDrone R4. And both devices contain the same sensor. The main difference is the R4 uses 5 of them, but can't get as close to the ground as the R1 sensor. I picked out an example measurement of parts of our test area for each. On the left side, you can see the color-coded map of the R4, and on the right side is the map of the R1. The GIS screenshot below shows the overlapping area of both records. The height of the sensors above ground was about 50 centimeters in the R4 measurement. What is really close for the device, for this device, and only possible under ideal conditions like our test field. While the R1 sensor was about 20 centimeters above ground. And that's why we have different amplitudes and signature diameters in the overlapping area if you look closely. The distance between the tracks, respectively sensors, is ½ meter in both measurements. Next slide, please. To take a closer look at the data, I selected the area outlined in white. And this track contains 3 significant signatures. Next slide, please. The first object on the left side is a 250 kilogram bomb buried at a depth of 1 meter 50. The second object is an explosive grenade 90 centimeters underground. And the third object is a projectile at a depth of 1 meter. And please note the signature of the bomb is only measured at the edge, as you can see. Next slide, please. Okay, here you can see the respective measured values. Of course, it wasn't exactly the same position, but close enough to compare. The original measured values are shown in gray and show the respective noise. The blue lines are filtered values as they come out of the MagDrone data tool. As I said before, the noise of such measurements is influenced by the drone and the environmental conditions. The environmental conditions are the same here, so you can see that the greater distance to the drone visibly reduces the noise. Here it is about plus minus 25 nanotesla in the R4 data to plus minus 10 nanotesla in the R1 data. What you can also clearly see are higher amplitudes and smaller wavelengths with the R1 due to the smaller distance to the objects. The different wavelengths is most noticeable in the bomb signature and the higher amplitude in the projectile data. And in general, the signal is smoother than with the R4. Next slide, please. So it is smoother, and this is also reflected in the color-coded maps, which you can see again in larger size here. Even if it is only a smaller section, the map of the R1 is cleaner, closer, and more detailed with the same processing settings in the MagDrone data tool. Next slide, please. So to summarize the advantages, the larger distance between sensor and drone leads to significantly less noise, and that the sensor can be closer to the ground allows the detection of smaller objects because they don't have such a big anomaly. But I also want to say, of course, the R4 also has advantages over the R1, but that always depends on the task. So back to you, Jonathan.
Great, thanks very much. I'm just answering trying to answer a couple of questions. So sorry, I was slightly slightly doing something else there, but yeah, okay. So look, thanks very much, Jan. Yeah, the conclusions are that it's giving, like you said, those amplitudes are obviously much higher. The noise levels are lower, and you can see that in the data. Much cleaner looking outputs. So that's really good, and it's really good food for thought. It is a really good system to bring into the market at the moment, because I'm talking to people all the time, and then they're always talking about getting, you know, as there's low noise as possible. It's always comes up in conversation with people. You know, how can we reduce the noise? When is this new SENSYS going to come along? And I you know, we've been talking about it for a long time. It's finally we've got it here. Knowing it's available for trials as well is great. And like I've mentioned, you know, put that date in your diary in September. I think I said 11th, didn't I? That date in your diary. Come along to the open day. We'll have it there. You know, obviously, if we need to do something before then, we'll arrange something between ourselves and SENSYS. But you know, come along, and we'll have the R4, the R3, R1 out. So yeah, come along to that day. Just to recap on a little bit, just to support customers. We're involved in solution sales, but we're a lot more than that. Those that know me should know that I'm really the service side of it is really important to me. Me trying to help you through that process of getting you to a business decision that you can hold up to and know that it's solid. You know, so we're helping with all those kinds of, you know, those sort of presentations, demonstrations, trials, you know, research and development projects as well. I've done a few of those recently as well. I'm really trying to get to the bottom of use cases. So yeah, just bear that in mind. It's a complete wrap. It's not just about trying to sell kit. It's not just about that. It's also about making it work for you guys. And this solution, I think, really is a really cool, a really useful tool in the tool bag. Yeah. So let's thanks, Jan. Thanks very much. Thanks for going through that. We've got a few questions that are outstanding, Jan. Yep. One of which is one of them, which is from Ahmed Tarjan, but he said, "Could you display the result of the compensation?"
The result of the compensation. Sure. Give me a moment. I have to share my screen again. Okay. So, of course, this is the result of the compensation. So, if you need to compare, I can.
Can you share your screen?
I thought I did it. It's loading. Okay. So in the meantime, I can do the processing to show the difference.
Yeah. It's
okay. Maybe I will try it again with the sharing.
Yeah, sorry, that was me. I was sharing my screen still. Okay, it should be okay now.
Okay. Okay. So
yeah,
do you
looks looking good.
See? Okay, okay. So in the meantime, I processed the data without compensation. So on the left side, you see the result without compensation, and on the right side, the preview you saw before. you have to look closer because you see the values here. So on the right side, the compensated version, you go from plus minus 50 nanotesla around 0, and here you have the original magnetic field values at about 49,800 and plus minus 50 from there. And so yeah, what you do with compensation is to calculate out the Earth magnetic field. And also you see here big signatures or how to say big trends in the 100 meter. So plus pole and a minus pole here in this case. So all that is be compensated out with the compensation.
That's useful. Okay. Okay, let's have a look at some of these. I might be able to answer myself. Yeah, we've got plenty of time, guys. So if you've got questions, please send them in now. We're going to go through them. We're going to go through them now. Okay, so that one's finished. How high does the R4 fly generally? Well, I think it depends on the application, and it depends on the targets that you're actually after. So,
and
for example,
on the terrain.
Yeah. So, I mean, Jan, do you want to just given your experience? I mean, I've got my view, but it's good to get it from you. Do you want to say something about how high does the R4 fly generally?
Okay, so at our test field, we can fly 50 centimeters, but I think it's not the general answer. So as I said, it depends on the terrain. So if you have a lot of high vegetation, you can't fly as slow, but I think a good altitude to fly is about 1 meter, and it's also a safe altitude. You can go really fast with 1 meter flight altitude. But it depends on the terrain, of course, and on the obstacles and whatever.
Okay. So hopefully that answers that question. We've done that one. Okay, what is the maximum elevation for this sensor to detect data, especially in case of high terrain area? It's difficult to remain at the same altitude, for example, 50 meters all the time. Sometimes the elevation reaches 100 meters in case of very high terrain location, in case of mineral exploration survey. So I think it's a question about mineral exploration survey, and that they tend to fly their flights quite a bit higher, don't they?
Yeah.
So I think what do you think?
So in general, you have to fly as close as possible to your targets, but so in mineral exploration, you can fly as high as you need above trees or whatever. So there it is not important to be as close as possible to the ground. And yeah, what's the question? How stable? Yeah, how stable? So in this case, you can't use the radar altimeter for the height, so you have to use the GPS height. And yeah, the stability of this depends on the drone, I would say.
Yeah. Okay. Okay, so the next question, I know the answer, but I'm going to pass it over to you. One of the questions that's coming in is how is the arm fixed into place? So at the arm of the R1, how is it actually attached to the drone? How is it fixed in?
There is a mount, a special mount for that. I don't know if I have a picture. Let me have a look. Yes, so I will share my screen again. Do you see it?
Yes.
So this is the mount. Here it's this belongs to the mount, and this is the R1. It's fixed into this part here.
Yeah. So what I can say, that hopefully this is answering another question as well, which is one of the questions was, how stable is the system when you're flying the R1? So
yeah.
I spent yesterday flying the R1, and where the test center is in South Holland here in Lincolnshire in the UK, it's quite an open space, so we do get quite gusty winds, and that it is pretty rigid actually. The way to fly the R1, as far as I can see, is as long as you're flying in a smooth manner, so he's flying smoothly, no jerks, no. It's very similar to the Echo Sounder in some respects, that you know what's going to happen when you jerk the drone. You know that the Echo Sounder is going to come up, and it's very similar to anything where you've got something that is dropped below the drone. You have to fly it sensibly in a way that suits the sensor. So I saw no problems in it was gusting quite, I think it was over 10 miles an hour yesterday to 10, 15 miles an hour. It seemed to hold up really well. And as long as I was flying in a smooth manner, the R1 pretty much maintained its position where we would expect, where it should. So yes, it is rigid. That heavy payload attachment, which is a similar attachment that's used on the Echo Sounder. I think it's the same one. It is really rigid. I mean, it holds the R1 really well.
Yeah.
So yeah, Jan, have you got anything else to add?
Yeah. So our experience shows that you shouldn't fly too slow. But from 2 meters per second and higher, it is very, very stable.
Yeah. Okay. So hopefully that's answered that one. They keep coming in. Okay. Is there a difference? This one is for you, Jan. Is there a difference in target location accuracy between the R1 and the R4? Do you have any test data?
Yes, as you have seen in the slide. So the difference is that you can be closer to the ground with the R1, and so you are closer to the targets, and that's why you have higher amplitudes and can detect smaller objects.
Yeah.
That's it.
So,
and of course,
so the actual targeting of the object it's the same sensor. So it's going to be
So the data processing and that's the same, yeah. And of course we can share the data.
Yeah. Okay. So the difference is the lower noise and just the higher amplitudes.
Yeah.
You're getting a cleaner, better, smaller, which theoretically means you can see smaller peaks, much more clearly identify smaller objects.
Correct. Yeah.
Yeah. Okay, that's that one. Okay, well, let's that one live. Okay. So how much knock can the sensor take? So we've got this sensor at the bottom of the arm, haven't we? Yeah. The sensor is at the bottom. The single flux gate is at the bottom of the arm.
Yeah.
We want to fly that as close to the ground as we can. And occasionally it might knock something.
Yeah,
it might knock, because we're trying to get as low as we can, aren't we?
That's no problem. We also did it in our test flights. You can touch the ground the whole flight if you want, but of course then it's more noise.
Yes.
But it doesn't destroy anything.
Yeah. So the answer to that question then is that it's pretty robust.
Yes. Yeah.
As long as you're probably flying it at 20 centimeters off the ground, and it's occasionally hitting the ground.
Yeah.
But mainly probably because of GPS loss or whatever. But yeah, but pretty robust. Hopefully that's answered that question. We've answered that one. Okay.
Graham Grover. So yes, the MagDrone data tool is available to download. You can find it on our website and maybe also on Jonathan's website. I think so.
Yeah, yeah. Did you also there's one, yeah. So I'll read this out. From experience of flying at a speed of 5 meters a second, the true terrain following sometimes lags behind. It does.
Yeah.
And when it comes to a hill, the sensor has a potential to knock into the ground.
Yeah.
Oh right, yeah, okay. So yeah, that's about understanding what terrain you're in, right, Jan?
Yeah, correct. So in this case, I would recommend not to fly 5 meters per second.
Yeah, yeah. There is a way around that. Yeah, there is also the other way of doing that is to so on the R1, the true terrain following is different to the R4. We locate it at the front of the drone on the gimbal mount, and therefore it's at a slight angle forward facing. So in theory, you should get less of a lag. But yeah, I'm guessing if you were flying the R3, you'd also fly it on the front as well. So yeah, but the angle should. Yeah, and I don't know how you feel. The R4 is different, isn't it? Because we look directly down in most cases, but you can. Yeah, what's your thoughts on that?
So I would say it's not a big difference in the angle between the devices, but it always depends on the terrain in combination to the flight speed. So yeah, but yeah. It's no big difference.
Certainly when I've spoken to SPH Engineering on this, and we have been playing over the true terrain following course on the test range, as you can imagine, to see what angles actually do better. And I'm getting a kind of feeling that there is having a slightly tilted true terrain following radar on the R4 does help. It does give you a little bit more time. So I would expect with an R3, if you're flying it with forward facing, then I would expect you to get to actually. I mean, again, at 5 meters a second, that's really fast. I mean, it's pretty fast. So
it depends on the terrain. It's okay.
Yeah. But okay. Anyway, yeah, I like Jan said, I think you've got to just think about the terrain. So hopefully we've answered that. Okay, that's done. And we've done that one as well live, so that's fine. May this sensor be used in mineral exploration? Can you see that, Jan? That question from Ahmed.
May the sensor be used in... So I don't know why most of the companies are using MagArrow. Maybe they have too much money. But of course, this sensor can be used in mineral exploration. Yes.
Yeah. I've seen some results from that, which are pretty good. Okay, so it can be used, and honestly, this is a question from myself, actually, I suppose, because I haven't really been involved in mineral exploration projects, and I'm in the UK, so it doesn't really come up every day. What's the process flow for processing the data for mineral exploration?
So, the process of flying. So
what for processing the data? Is it the same? Are you using the data tool?
Yes, but as I mentioned before, you have to use other settings for compensation, for example, because in mineral exploration you want to see the whole field and not small anomalies, and so that's why you have to handle the compensation a little bit different. But
Okay.
in general, it's completely the same. And of course, you don't have a track distance of 50 centimeter, but you can have a track distance of 10 meters or whatever, because you want to see big structures.
Yeah. Yeah. Okay. So the answer to that question is that yes, it can. There's some compensation adjustments, but yes, it can.
Yeah.
Yeah. Okay. Okay. Is there a recommend height you would fly above vegetation like grass or anything comparable with a sensor? I mean, you just fly a normal height. I mean, you know, if you've got grass, then you're flying a meter above that. Again, I think what Jan said earlier about the terrain. You've got to take in the terrain into account. You need to take in the vegetation into account. If you're flying over grass and then you're going to go into a bush, you need to be aware that that's going to happen. So 9 times out of 10, the object detection on the drone it will stop you from doing that. It will see that bush, but like I said, you might need to, if you are in those kind of vegetation states, in those kind of situations, sorry, it might be worth getting an ODR. Because like I said, it's a known issue with certainly with the M300 and the M350, it's a known issue, just to be on the safe side. But yeah, take into account, like Jan said, but do your due diligence. If you need to fly an ortho mosaic before you go, it might be worth doing some kind of pre-work before you actually go and fly your mission. In what terrain do we recommend 5 meters speed with the R1? It's like, I guess it's a little bit different than the R4, but because you're not horizontal, you're flying 5 meters a second and above when you've got smooth terrain, aren't you? It's a smooth terrain. The true terrain following has a half a second delay, as far as I'm aware. You need to make adjustments for that. So where you have sudden changes in elevation, sudden changes in terrain elevation, that is not good. The arm it will go back. It's not like it's fixed. So if you like we mentioned before, if you do happen to hit maybe a clump of clay or something that's above the ground level, the sensor will just move back, and then it will just move back into place. That particular data point or that area won't be very useful, but at least the rest of it will. So ideally, you want to be taking the minimum that you should be flying at into account, so you don't get that kind of thing happening. Jan, would you agree?
Completely.
Yeah. Is it possible to test the ODR at the open day? Yes, it is, and we intend to do that. Okay, so that's that. Okay, I think that's all the questions. We've answered all the questions. Okay, look, Jan, thanks very much for your time today.
It was a pleasure.
I think the Q&A was good. I think we've got through quite a number of questions there. Goes without saying, everybody, if you would like to contact me afterwards, please, I think most of you probably got my emails. If not, info@jbuas.co.uk. You can go on LinkedIn, follow us on LinkedIn, see our trials and demos that we're doing. Obviously, now we've got the test center, we'll be trying to post up as much as we can. Yeah, technical questions, obviously, we're backed up by SENSYS. We can get you the answers. If I don't know off the top of my head, then that is something I can just reach back into Jan and his team. So yeah, thanks very much, everybody. I really appreciate your time, and I can see we're 10 minutes over, but I think it was very well worth it. So thanks, everybody, and I'll see you at the next webinar. Thank you.
Thanks. Bye.
Thanks. Bye-bye, everybody.